So we were on IEEE 802. IEEE 802 means all standards, almost all local area standards developed by IEEE. That includes Wi-Fi, that includes Ethernet, that includes Keppen ring, and there are many others up to 21, 8, 3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 21, 23. I think it's up to 23 right now. Anyway, all of them use this address, 48-bit, which is used with the colon marks. And when you go to IEEE, they give you 22 bits. And so you get 2 raised to 22 addresses for $1,000. And then you can start assigning from 0, 1, 2, 3, 4, 5 all the way to whatever number you want. The first 2 bits are reserved. The first 2 bits are, the first bit is for individual or group. If it is 1, that means it is a multicast address. And those are again assigned by IEEE. And so for example, to all the bridges, you want to send a message to all the bridges, there is a particular multicast address. You want to send it to all routers, there is a multicast address. To all DHCP server, there is a multicast address. So there are multicast addresses for many different functions. So they will all have one first bit equal to 1. Second bit is universal or local. 0 means universal, 1 means local. 0 means individual, 1 means group. So if that bit, second bit is 0, that means it is globally unique and assigned by IEEE. If that bit is 1, that means it is locally assigned by the manager of that building and it has no global meaning. So that OUI, everything else is meaningless if that second bit is 1. Alright? And at that time when we were doing this Ethernet addresses, some people really wanted the addresses to indicate location. They wanted it to indicate the building number, the floor number, and the closet number. So they said, okay, you can do that as long as you put this bit 1 and then you can put whatever you want in the rest of the bits. Right? Those things are all gone. We no longer use any location in the addresses. Those were demands of the day, but they really failed. So these are unique. Basically we use globally unique, which means this bit should always be 0. Now the only exception is the broadcast address. Broadcast address is all 1s. The first bit is 1 means what? It's the multicast address, it's a group address. The second bit is 1 means, but it is not. Second bit is 1, that's an exception, it is a universally multicast address. So basically that, as long as all bits are 1, that is a broadcast address, everybody is supposed to listen to it in every place. Is that clear? So it's not a local address. Broadcast address is not a local address, it's a universal address, but that bit is 1. It's very easy to check for all 1s than to check for all 1, 1. Alright. Now bridges. So the way Ethernet initially connected was that you had this wire and everybody tapped onto the wire, and then if you wanted to connect 2 wires, you put a bridge in between, and the bridge will listen to all the traffic on this side, and then it will, by listening to the traffic, it will understand who is on this side. Similarly, listening to the traffic and looking at the source address, it will know who is on this side, and when it saw a packet going to a station which is on that side, it will pick up and then send it over. So the bridges are called self-learning. Self-learning means they learn, they become smart just by looking at the traffic. You don't have to program them, telling them where the routes are, where the things are. Okay? And you, please close the computer. Alright? So the bridges are self-learning bridges, and they learn by how they learn the location, source address. They look at the source address and they make a note of it. So all the addresses are put into a table that you see on the source addresses, so then you know in this big table who is on which side. So bridges, they monitor all frames on LAN A, pick up the frames that are for the stations on the other side, retransmit the frames on the other side, knows or learn about the addresses, and that is why we have self addresses, they make no modification to the frames. So they don't put their address as the source address. Even though they are transmitting on the other side, the source address is still the same as before. Okay, so no modification. They are totally invisible. Provide storage for frames to be forwarded. If the other side is busy, they will keep it in the queue. Improves the reliability because now you have less nodes per wire. Improves the performance because you have less collisions, and improves the security because you can prevent the traffic from entering a particular wire, and may provide flow and congestion control. So again, this was a debate at the time when we were discussing the standard. Some people wanted bridges to do flow and congestion control. So IEEE standard allows that, but nobody uses it today. Yeah. So there are many things that we use. We use the word repeater, hub, bridge, router, switches. All right. So let me explain. So yeah, your question was whether bridges are same as switches. The answer is yes. In the beginning there was a slight difference, but now we said bridges were 2 ports, switches were multi-port, but now we don't, because there are no bridges left actually, only switches left. So we use switches. So repeater, what is a repeater? Repeater is a physical layer device. What is a physical layer? Physical layer doesn't really know the packets, it doesn't know the frames, it doesn't know, all it knows is the bits. A bit in is a bit out, that's the physical layer. So if you have an amplifier, a digital amplifier which takes a 1 and sends out a 1, it takes a bad one and sends out a good one. You know what is a bad one and what is a good one? A bad one is all crooked, a good one is very square. Alright, that is a repeater. So it's a 5-layer device. Hub is a multi-port repeater. So if you put a hub, you can connect many things. One bit comes in, one bit goes out. A bad bit comes in, a good bit goes out. That's a hub. You cannot buy a hub these days, but 10 years ago you could buy a hub which looks almost like a switch. You connect 10 computers to it. But the difference is basically it's a physical layer device. It doesn't do anything. A bit comes in, a bit goes out. If 2 people send a bit, both people's bits get mixed up, collide, and the collision is sent out. It doesn't do anything. It doesn't send jam, it doesn't send anything, but the 2 stations will collide and they will send out a jam, and these jams will come in and the hub will send it out. It's a physical layer device. That's a hub. Now this is not very clear in the book, so please listen carefully. Bridge or a switch is a layer 2 device. Layer 2, the difference between layer 1 and layer 2 is layer 1 knows bits, layer 2 knows frames. Layer 2 knows frames, it can calculate CRC, it knows a bad frame from a good frame. Layer 1 doesn't know a half frame from a full frame, doesn't know the beginning of a frame or the end of the frame. It knows only bits. Right? Everybody knows the difference between layer 1 and layer 2. Layer 1 is a bit level device, layer 2 is a frame level device. So the bridges look at the whole frame. If the frame is good, they look at the destination address and the source address. If the frame is no good, they throw it away. Alright? That's what we call a switch today. Collision doesn't pass through. If they see a collision, that's not a frame. Collision happens only on one side of the switch. It doesn't go to the other side. If it is a hub, the collision will go to all the hubs. So hub actually basically extends a wire. If you connect 2,000 stations to a hub, what will happen? What will go up too much if you connect 2,000 stations to a hub? Collision. Lots of collision. If you connect 2,000 stations to a switch, the collisions will not go. But what will go is the broadcast. If somebody sends a broadcast frame from this side, it will go to all the other people because this is a complete frame, CRC passes, it's a multicast frame, it will broadcast to all the sides. So to stop that, we need a new device which is called a router. Router is a layer 3 device. Router is a layer 3 device. It only looks at the layer 3 addresses to begin with, means it looks at the IP addresses, not the MAC addresses. But it also, because the broadcast frames do not have an IP address unless they have IP multicast, Ethernet multicast will not get through. right? Ethernet broadcast will not get through, and so they stop the broadcast storms. If you put the whole campus on one LAN, on one Ethernet, there will be a broadcast storm. You know, somebody sends out one broadcast, and then the whole, it makes 50,000 copies are made, and somebody sends out another one, another 50,000 copies are made. There will be lots of broadcast, right? So broadcast is stopped by the router. So everybody should understand the difference between a repeater and a hub, a switch and a router. When you go to buy, if it says switch, and you go to buy to Best Buy or Walmart or whatever, a switch, that's a layer 2 device. It doesn't know IP. All right? It cannot. If you go to buy a router, it's a layer 3 device. It will probably have a built-in DHCP server and other things nowadays. They make NAT and so on and so forth, everything in there, right? That's a router. That's the difference between router and a bridge. Bridges are very cheap. For $5 you can find a megabit or a gigabit switch. $10. Routers are expensive. For $50 you can find a 10 megabit router. A gigabit router probably is $100. Yeah, go ahead. Yeah, $1,000. Huh? Hub and, okay, so again one more time. Hub and the repeater are layer 1. Repeater is just 2 port. Hub is multi-port. Right? So here is a picture here. Hub. So we connected these 3 nodes by hub and these 3 nodes by hub, and we connected these 2 hubs. This whole thing is what we call one collision domain. Anybody in this domain, when they speak, they can collide with the other person in that domain. But they will not collide with the people on this side, because these are connected by a bridge. A bridge bounds a collision domain, but the broadcast, it doesn't bound the broadcast. Right? A router bounds the broadcast domain. So this is called a LAN, and this is called an extended LAN. Because as far as the router is concerned, this is still one subnet. Right? So this is called extended LAN, and this is a LAN, this is an extended LAN. An extended LAN is one broadcast domain, a LAN is one collision domain. Now, so today we don't have hubs. So basically what happens today is, basically there are no collisions whatsoever. All this theory that we taught you about CSMA CD doesn't really used in the latest devices. In the older devices it is used. So every computer has to implement it. It is implemented in every computer, but nowadays we connect our computer directly to the switch, and there is only 2 nodes on that network, on that LAN, in that collision domain. There are only 2 nodes, the switch and you. And you do not collide because there are 8 wires, 4 are used by you and 4 by the other side. So the continuously traffic can flow full duplex on today's switches. Today's switches are full duplex, and so there are no collisions, there is no CSMA CD, there is no limit of 2.5 kilometers, and everything that we taught you about Ethernet is for the old devices. And the irony is that everybody has to implement all that old stuff, because you could have one computer in the whole building which has that old Ethernet, and they want to make sure that it also talks to everybody else. So everybody implements CSMA CD, everybody has this collision detection, jamming, and back off and everything. So everybody understands how these things have changed. Next thing is ARP. Basically, there is a mixture here. Some packets come in and they are coming with the IP addresses, but when we send them on Ethernet, we have to know the Ethernet address. Right? So how do you find out whose IP address is whose Ethernet address? Right? And for that there is a protocol called address resolution protocol. So given one address you can find the other. Given the IP address you can find the Ethernet address. Given the Ethernet address you can find the IP address. And the protocol is very simple. You just ask, you broadcast a request. You broadcast what is the MAC address of this IP address. Alright? and somebody who knows the answer will say the MAC address for this IP address is this. Done. Once you know the MAC address, then you just send the packet which was for that IP address to that MAC address. It will go to Ethernet. On the Ethernet, bridges will send it to the right place, and the right host will pick it up and open the packet and find the IP packet inside the Ethernet. Yeah. And there is all kinds of ARP attacks where you could say, well, I am X and I am Y, I am the president, I am the bridge, I am the router, whatever you want to be, you can be. Right? You could be any IP address you want, and the packets will be sent to you, and then the other guy will be left into a black hole. And so there are attacks. The only reason it works is because this is all done inside a LAN. So another definition of LAN is single domain of ownership. All the people whose computer are on this LAN, they somehow belong to one company. Right? So they're not going to play games like that. Hopefully they will, otherwise will be fired or something like that. So that's why it works. Now, ARP answer can be given by anybody. It doesn't have to be the host. Routers give most of the answer most of the time. Yeah.
What if different answers are given by different?
Yeah, obviously then you are in trouble, because then one person is wrong.
I mean, like, what if, does it send it to the first one it gets, or?
No. So the thing is, here's the thing. You broadcast your request, the response comes back to you, right? And if you get a response, you probably are going to use it. You're not going to wait for the second one. Now later on, second one comes. I think what will happen is most likely you will override the previous response, and now you will start sending the new one. I mean, there is no other method, because you might have changed your MAC or IP or something. Who knows? And these addresses can change. The thing is, your MAC address never changes, but IP address is changing. You take this computer, it has an IP address. Take it outside, there's a different IP address. Okay? All right. That brings us to the end of Ethernet and ARP. And Ethernet and ARP. So these are the four key conclusions. First is CSMA CD, means carrier sense, means listen. Multiple access means share. And CD means listen while transmitting. So listen while transmitting and stop on collision. That is what collision detection is. And use a truncated binary backoff. So what is binary? Why it is called binary? The backoff range goes up by a factor of 2 every time. And why it is truncated? You stop at 10. After 10 attempts. You have 16 attempts total, but after 10 attempts the backup range doesn't go up. Ethernet uses 48-bit addresses. First bit is unicast multicast, second bit is universal. 22 bits are OUI. OUI, IOU. You know what is OUI? OUI is organizationally unique identifier. That tells you the manufacturer of that equipment. You can look at any iPhone, you can look at any computer, you can look at any device, you can figure out who made it by looking at the Ethernet address. Okay? ARP. ARP is used to find the MAC address for given IP address and vice versa. Yes, so given a MAC address, you can find what is your IP address.